All right, welcome to Operations Research. This is Math 317. As you can see, the technology is already acting up and it's not even the first 5 minutes of class. So for those of you who are sitting here, you will be in perfect view. Unfortunately, I will keep seeing if I can swivel things around so that it will only get the screen. I am trying to record it directly through my computer, and hopefully that will work as well. All right. So there are handouts. If you have not gotten the handout, please let me know. It is also available on the webpage. Do we have any handouts left? Okay. So the enrollment in this class is very different from what the registrar told me. This is not the first issue today. The second issue, in fact, the first one was that I did not have access to this building, nor did my colleagues in math stats. So hopefully we will have class again on Monday. We're not quite sure yet where or who will be teaching, but we will figure this one out. A couple of rules. First of all, cell phone policy, you get a vote. If someone's cell phone goes off, there's either a pop quiz for the next class, or whoever's cell phone goes off provides Dunkin' Donuts and snacks for everybody. Donut. My phone number is 617-835-3982. My son just got a cell phone and my daughter is encouraging him to try to call me during the school day. So we will see if he's able to succeed at any point.
Does that mean you bring us donuts?
Yes, that means I bring you donuts, yes. So in fact, well actually I'm not going to tell you how to do this. That is not something I want to help you with. All right, so what I want to do today is just talk a little bit about the basics of the course. It would be nice if the clicker worked. All right, so let's see. There we go. Okay. So the main topic is going to be linear programming. There's a lot of different things we can study, and such as, for instance, how to align clickers and computer screens. Let me try taking the cube and seeing if I can physically force it to stay in place. No, it's well, somewhat. All right. So. Anybody have any heavy books that they don't need?
Yeah, I do.
No, that's not right. For those of you who are coming to probability later today, this is a good heavy book. All right, so let's see if this is enough to really fix it in place. Let's see. All right. So hopefully most of you have taken linear algebra. There's not that much we need from linear algebra for this course. The main thing is, system of equations. You have variables, you have coefficients, and you want to try to find what solves it. Typically, you work with square matrices. There's a lot of nice properties with square matrices. You have your eigenvalues, your eigenvectors. You can look at non-square matrices. And in a situation like this, you will frequently have either an overdetermined or an underdetermined system. If you have an overdetermined system, it's unlikely you have any solutions. If you have an underdetermined system, then you might actually have many different solutions. And this is where the chance for optimization comes into play. That when you have more solutions than just one, you can say, well, which solution is best? Best in what sense? So one of the biggest issues of this class is always going to be, what is your metric for success? US News and World Report or Forbes, which do you like more? Yeah, this campus, it's US News and World Report, because according to the metrics in US News and World Reports, Williams comes out #1. I will not say, since this is being recorded, which metrics I prefer. But depending on the metrics you choose, you can get a different answer. If you are trying to buy a house, what do you care about most? Do you care about location? Do you care about size? There's a lot of people who have houses that are very large, but they are quite a good distance away from where they work in New York City, and they spend a lot of time commuting. Because they'd rather be in a good school district and have a large house than have a small house and be closer to the city. So you have a lot of trade-offs. So we're going to talk a lot about optimization, about linear programming. What can you do when you have more than one possible solution? What additional constraints can you put on? We're going to hopefully have a bunch of guest lecturers. One of the first ones is Francis Su from Harvard Mudd. He'll be talking to us about rental harmony. So for those of you who are planning on graduating this year, how many people do we have? Okay, so some of you may be looking for people to share apartments with, in which case you really have to decide, how do you divide up the rent? And so not every room in an apartment is equal. And so there's a lot of really good mathematics behind that. Another good application, this is to the theory of divorce. I'm hoping that this will not be useful to you later in life, but just in case, I will talk a little bit about how you can use this and how you can potentially game the system. So a lot of this is asking the right questions, okay? This is one of the most important skills to learn. Do not be afraid to ask a question. Often, if you are not understanding something, almost surely someone else is not either. When I was teaching differential equations, we don't require linear algebra as a prerequisite, which I think is wrong. But junior faculty, first year at Williams, no chance of getting that changed. Okay, differential equations without linear algebra, fine. But you gotta do systems of differential equations. If you don't, it's just a waste of a class. So I want to know how many of my students do 2 by 2 matrices. Silence. So everybody's comfortable with 2 by 2 matrices. Nobody wants a review of 2 by 2 matrices. Okay, well we had clickers. Out of curiosity, how many people want a review of 2 by 2 matrices? I'm not gonna report back to the class, I'm just curious for my own interest. 43, I never said I wouldn't tell all the classes. 43% said that they would like a review of 2 by 2 matrices, and not one person was willing to raise their hand. So almost surely, if you raise your hand and ask a question, you'll go, oh my God. But they'll be very grateful that you did it. So I'm strongly encouraging you to please ask questions like that. We will talk a lot about modeling problems and how to analyze them. So I actually have a lot of experience in applying math to solve real-world problems. For some of them, the recording system will have to malfunction for me to talk in great detail about them, but I'm happy to go over how do you actually use math in the real world. You do not have to come up with the best answer. You just have to do better than what is being done. That's often a very low bar. And so I tell freshmen that you often have enough to be making legitimate contributions already. So last year I actually had 5 students, 4 of them were freshmen, working with me on a multi-million-dollar Major League Baseball lawsuit. And eventually we'll talk about that and some other problems, that if you can just do some basic modeling and stuff like that, you're gonna be in great shape. Whenever possible, I will talk about trying to find elegant solutions. This is not always possible. A lot of times, how many people here are econ? Okay, so a lot of times you have to resort to massive simulations to get a sense of what's going on. If you can get a closed form solution, this is wonderful. You can try to get a sense of how things behave. All right, the last is, if I'm dead, I'm not writing a textbook, otherwise I'm writing a textbook. So if anybody is interested in writing a book, please let me know. I have several projects that are ongoing right now. Obviously, the book that you're reading is a completed project, but there are other things, and if you are interested, it's a really good exercise as to how you write material for a general exposition. So years ago, I was working on the probability book that the next people in this room will be using, and I was doing an independent study. We spent an entire hour on the first sentence. But we got better. Your second sentence only took us, half an hour. But it's a really important skill to think about how do you convey information. So later today, I'm going to show you a couple of plots and ask, what can you tell me from this? Is everybody here a math or a stat major? Or thinking of being a math or stat major? Anybody not? Okay. Any of you considering a career in mime? If so, speak. Oh no, that would be wrong to have you speak up. So we are the only department left on campus to require students to speak before we let them graduate. You have to give a colloquium talk. And this is because we know how important it is to be able to communicate. And so a good chunk of any advanced class along these lines is how do you present information in such a way that you can convince people to do what you say. And so we will talk a lot about that. All right, so types of problems. How many of you have heard of the diet problem? All right, so imagine you're a dictator of an evil republic, well, probably not an evil republic, let's say evil nation. And you want your people to stay alive, but that's basically it. They just need to have enough energy to do things for you. So you might want to have the minimum sustainable diet possible, the cheapest thing possible. Now, this is an extremely important problem in several developing nations when you have limited resources. This is the positive spin on things. What do you plant? How do you plant it to maximize the benefits to the people? I had a couple of students who did a wonderful project on that years ago where they actually, be careful because this is recording. I won't say the details of how they did it, but they were able to get all the information from Stop and Shop and actually assemble the cheapest possible diet that you could get from Stop and Shop that would keep you alive, and brought it to class. Fortunately, I was on some medication and was not able to eat it because I wasn't sure how it would interact. But this is a very simple linear programming problem. The initial solutions to it had some incredible absurdities as people were realizing, oh yes, the way this is inputted, some things were routed into the program and we should not be putting in this many gallons of this or that. And so you always want to have a sense of, is your answer reasonable? So when you're looking at it, do you have a rough feeling for what it should be? There's a lot of things I can talk about. Let's say you own American Airlines. What is your objective if you own American Airlines? It's
Sell flights.
no.
Cram as many people.
No.
Make money.
Make money. As a default, if I ask you, if you own X, the default answer is to make money. How do you make money? Selling airplanes, cramming people in. Okay. And then you also have a lot of constraints. You know, if pilots have flown for so many hours, they need so much time on the ground before they can fly again. How much time can you have between yes?
Just to push back on that, to make money. Isn't that not always the case? Is Amazon the example? Someone who's in debt or making no money, paying no taxes because they have losses, but they're up.
Well, but then you have to look at long term. And sometimes if you own a major league sports franchise, this could be an example where you're not trying to make money, you're trying to give back to the community, and you're trying to just enjoy the championship. We'll say almost always your goal is to make money if you own a company. So you have a lot of different constraints. Let's say you own a movie theater. What is your objective? Make money. So what movies do you choose to show? When Star Wars The Phantom Menace came out, I'm afraid to ask how old you were when this was. This was the first Star Wars movie in decades. We were excited. You know, I was able to arrange a deal with a local movie theater where they gave me 300 tickets, so long as I had, you know, one person in line for every 10 tickets I bought. We did not realize what the movie was going to be at the time. We were very excited. George Lucas had tremendous control when he was getting ready to send out Phantom Menace. And he told theaters, you know, if you want to show our movie, you've got to guarantee your biggest 2 screens for at least 8 weeks, and you have to have this level of sound system, because otherwise you won't appreciate the subtleties of Jar Jar. And he put all these constraints, and most people said, yes, 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 yes. And a couple said, no, it's just not worth it. And you have to look at the revenue. A lot of movie theaters, the way it's structured, you get more of the percent for each ticket sold the longer the movie's been out. So you love sleeper hits like Blair Witch, which start off small and move up. But big box office smashes that start high and go down, where does the movie theater make most of their money in that case? Exactly. Right, reasonably priced Cokes and popcorns, exactly. And so a lot of movie theaters, especially during the summer months, will show old classic movies either for free or $1. And oh, air conditioned, you know, let me come in, buy some popcorn and soda. And that's how they will make their money. So there's a lot of good mathematics that we can use to solve stuff like that. If you like things a little bit more theoretical, famous, probably a little bit older than Fermat's last theorem, is sphere packing. You know, what is the best way to pack spheres? And it turns out that the answer that everybody expected is right is the one that's right, but it was not solved until after Fermat's last theorem. So it's older and took longer to solve. And when the solution came out, there was a lot of dispute in the community as to, is this a solution? Because a huge part of it was a computer analysis. Now, a tremendous amount of work, including linear programming, was done to reduce it to like a 150-dimensional linear programming problem, which the computers could then attack. But then the question is, how do you know if the final result is trustworthy? So there's a lot of great applications for this material. All right, so just some of my experiences. So my wife is a professor of marketing, and through her, I've met a lot of marketing professors who are like, oh, you're dating a math guy, can we talk to him? And so I've actually been able to work with a bunch of marketing professors on a variety of projects. So if you're interested in stuff like this, either my wife or I are happy to talk in greater detail. When I was a very newly minted PhD, I got an email one day that began, greetings, my name is David Kelly. I'm a senior criminal investigator at the Internal Revenue Service. And so, you know, 5 minutes later, I finally, you know, built up enough strength to read the next line, which is, I just read with great interest your recent paper in Acta Arithmetica. And yeah, I'm such a newly minted PhD, the fact that anybody's really getting my papers to begin with. Why? And so I do some stuff on Benford's law of digit bias. And it turns out that this has a lot of applications to detecting tax fraud or image fraud and stuff like that. And then the last one, which as I've mentioned earlier, is sabermetrics, mathematics, and sports. I've had students working with me on consulting projects for Major League Baseball, where we have been tasked with dealing with some medical issues where, former all-star claimed that the surgery was botched and their career was ruined. How much should they be paid? My favorite was the person whose surgery, it was done so badly, the hospital said, yeah, we screwed that one up. When the hospital doesn't even try to defend the surgeon, the surgery was done poorly. But the person had pitched less than 2 innings in college and was claiming that he would have been a major league pitcher. How do you estimate with that little data? So again, I'm happy to talk about projects like this. If there are things you want me to incorporate into the course, let me know. I'm sure you're all eager about grading. So right now, here's the rough outline. 15% homework, 5% class participation. That means coming to class prepared. Midterm, 40%. Final, either the final exam or the final project, 40%. One of the last times I taught this class, we had 6 students working beautifully with Berkshire Medical Center. And the people down there were thrilled with the work the students were doing and wanted them to do more. And I told the students, how'd you like to have no final and just keep working with the doctors? And they're sold. So if you can find a project that is really good, especially a project that is working with a local company or something like that, and I can try to help you with stuff like that, I am quite happy not to have a final for you guys and have you guys spend your time working on the project. Depending on how well things are going, that even means potentially no homework at some point. Just every waking moment, we want you working on this. So especially for those of you who are interested in the business challenges, this is a wonderful opportunity for something like that. Happy to talk more, but the goal is to show you how you can use this math to do things. A lot of times there's this feeling that if it's not the most advanced mathematics, it's not snootiness, right? How many of you are familiar with the Battle of Midway? Right? One of my favorite stories of military history. So at the start of World War II for the US, surprise attack on Pearl Harbor, things are not going well for the United States in the Pacific. The Japanese are winning the battles. They have more aircraft carriers than we do. Aircraft carriers turn out to be the key ships in the war. We have decrypted most of the main Japanese code. And we intercept one of their messages that says the Japanese are planning to attack AF-15. And so they go to Admiral Nimitz and say, we're pretty sure the Japanese are going to be attacking here on the following date. Pretty sure? Are you sure AF-15 is Midway and not Australia or Hawaii or the West Coast? We're pretty sure. I want a little bit more than pretty sure before we move all of our forces there for us, a counter. And so how do you finish the analysis? Well, one possibility is you contact Japan, call Tokyo and say, hi, we're having a little trouble with one of your messages. Could you? No, not going to work. Commander Rochefort had a brilliant idea, one of the smartest ideas I've seen in my life. On a secure channel, they contact Midway, and they tell Midway to break one of their water pumps. And then they tell Midway, either in a message in the clear or in a message in the frequency we know the Japanese have cracked, because it's a low priority message, just when you're giving a bunch of reports, just mention that you have a broken water pump. A few days later, the US intercepts a Japanese encoded message, which says we've intercepted an American message from Midway. Except they don't say Midway, they say AF-15. We've intercepted a message from AF-15. AF-15 has a broken water pump and will be out of fresh water in 2 weeks if it's not replaced. Absolutely brilliant. So when you're trying to find a project or something to do, it doesn't have to be at the level of the next Amazon or Google or $1 billion monstrosity. If you can find a way to apply mathematics and make things better, that's wonderful. That's the goal for something like this. All right, so most of the prereqs is linear algebra. If you've seen some analysis, if you've seen some programming, that's a plus. This is not a co-listed class. This is not a computer science class. If you want to do some programming, absolutely encourage it. Any language you want to do is fine. I go all the way back to Fortran. I don't think anybody else still wants to use that, but we can talk about different things. Depending on what language you use, I will almost surely not be able to help you. with the actual coding, but I can help you with the theory of the coding and just the pseudocode. Okay, so if I'm in my office, it's office hours. Google is now getting stronger in terms of letting people remotely sign on from, I used to just say, here's a Gmail account, you can use it to send me anonymous information. Gmail is now not letting people sign on, so I'm no longer sure if this is possible. But if there are any issues, please, if you don't feel comfortable speaking to me, just send me an anonymous email, put something under my door. Happy to talk to you about various things. All right. The course webpage is using the greatest technology from the 1990s. I have not updated my software. It's actually a pain in the ass every time I get a new computer because I have to make it compatible again. The advantage is when William sends out an email saying we've now changed the course management program we're using, I can just hit delete. And I don't have to worry about all the errors and all the bugs. So I realize the web page looks old, but all right. So this must be important. This is at least the second time it's appeared. Okay. So here is some advice from my brother. 3 points of wisdom he has distilled from his college days. Party less than the person next to you. So I think everybody has at least one person next to them. Take advantage of office hours and mentoring. When you leave the purple bubble, you are not going to have the same access to support as you have here. I've been at schools where office hours were 8:30 a.m. the day after homework was due. And the students got the message, okay, you don't want to see us, we understand. We are here at Williams because we actually like teaching, we actually like talking to students. Unlike most of your professors, I am not going to try to get to know you. What does that mean? What's your job?
To reach out.
To reach out, and what's your name?
Porter.
Porter, thank you, Porter. It's to reach out and make sure that I get to know you. This is how the real world is typically going to function. You have to get noticed. So if you read Michael Uslan's speech, one of the big points he has is what was he able to do to get noticed. And so I strongly encourage you to reach out. I'm happy to grab a coffee, a lunch, go for a walk. Not watch a Red Sox game on the way this season is going, but take advantage. For those of you who are not graduating this year, the more professors you know, the more likely it is that somebody will have an opportunity to go, oh, so-and-so would be great for that. And the last is learn how to manage your time. No one else wants to. If you can dispose of something quickly, dispose of it quickly. Don't let it sit in your inbox for a while. Get things done and out. One of the things I would add, which he didn't include, is have good file names for things. Report.pdf, paper.pdf, resume, cv.pdf, those will be deleted. Okay. You really want to have good notation. Okay. How many of you have had an interview already? Okay, good. If you've never had an interview, I'm happy to do a practice interview with you or just talk to you a little bit about how to handle an interview. Depending on how the interview is being done, there are many different ways you can prepare for it and go about it. The last is, I believe everyone here is taking at least one other class and maybe has some extracurriculars and whatnot. So if by some strange chance you actually have multiple things in your life happening at the same time and you need a deadline to be moved, please let me know. That does not mean an hour or 23 hours before something's due, let me know. It has to be at least a day in advance. Right? If it is a true tragedy or whatnot, and I don't want to go through right now and list all the bad things that can happen to you, sure, happy to consider it. But as a general rule, you should not be waiting to the last minute. You should be planning and making sure things get done on time. If you're going to need an extension, know well in advance. Okay, this should hopefully be a link to an online linear algebra textbook. I'm not going to need that much from linear algebra, essentially just solving systems of equations. The few things we need, I will be proved. How many of you remember the rank nullity theorem? Yeah, not going to use that. Eigenvalues and eigenvectors, no. We're going to really focus on other parts. So the amount of linear algebra we need is not going to be too extensive. What we will need at times is perspectives on how to prove things. Okay, so a bunch of useful links. So I have a link here to some handouts on LaTeX. If you go to my webpage and you take any PDF extension, any file that I've posted, and change that to .tex, you'll get the source code. There's also links here to slides, to mathematical tutorials, to videos and stuff like that. Okay, so a couple of examples. Any football fans here? Okay, who can tell me what this is? Oh, I should not go here. Who can tell me what this is? Anybody remember?
Is it the missed field goal run back?
Yes, it is the missed field goal run back. So Auburn and Alabama are huge rivals. There was regulation, it was their big game, and unfortunately for Alabama, they had the ball, but time ran out. And then their coach protested and said that there should really be 1 second left. And so they said, fine, we'll add 1 second to the clock, and they will go and begin to a 57-yard field goal kick. So they're trying to kick 57 yards to win the game. He goes short and picks it up and running and running and running. All right. So why am I showing this? This is a class on optimization, on doing things well, doing things efficiently, taking advantage of opportunities. Alabama said, well, you know, look, we've got 1 second left. We could either do a Hail Mary pass, we could try a long field goal kick, or we could just sit on the ball and go for overtime. I said, we'll go for the long kick. We think we have a better chance of getting that to work. Auburn is defending this. And they go, well, you know, the odds of getting a 57-yard kick, that's minimal. Let's set somebody up and have them prepared, hopefully, to run it back. So it's always being prepared for whatever opportunities may come your way. I'm going to skip some of this. This is stuff I've done with WICMA. Scheduling baseball tournaments and swim lessons. I want to talk a little bit about inefficiencies of location. So this is the Young Mathematicians Conference at Ohio State. I spent 6 years working in the restaurant industry, and inefficiency bothers me in general. Inefficiency in food service bothers me tremendously. And so I had them change how they were serving lunch so that you could actually have people going on both sides of the tables and not have the tables flush against the wall. Very small change, just push them out a little bit. Fortunately, I had a large number of Williams students who came with me. It's like, we were able to just move ourselves. I don't think, was that your year? Or that is, okay, I thought it was before your year. This is one of the old lickety splits. Any issues here? Yes.
The soda is far back from the counter, so you can probably steal without getting noticed.
So, publicly, I have to say, I'll face this, I'm glad that you are thinking of ways we can improve security. That is absolutely one of the issues. It's over there. Yes.
It's in the sun.
It's in the sun. So for me, the main issue is the sun. Stealing is another issue. But the fact that you've got the cold sodas where the sun is beating down on them, rather than putting them in a nice shaded area. Yes.
At that point in time, did people go through the line like this way, like where that guy's standing in back?
There's been so many iterations. I think we just came up the stairs like that.
So that guy's
That's
just
fine.
doing something.
That guy's just waiting. He's next. He's in standby. All right. This is from the Pittsfield Suns. So my son was probably around 4 years old, and I took him to a Pittsfield Suns playoff game. And we're sitting right behind home plate, and I go, Kim, we've got the best seats in the house. Right behind home plate, we can see everything, can't get hit by a ball, perfectly safe. The very next pitch is fouled off and hits somebody 10 rows behind us, it's sad, in the eye. He has to go to the hospital. His 3 children are crying. Kim starts to cry. I said, look, we're safe. We're so close to the net that there's no angle for the ball to get us. I never said everybody else was safe. And so the idiocy of having the net go up there and just having this gap. There is a lot of inefficiency out there in the world. Almost surely there is some inefficiency out there in your life. I think one of your assignments is to try to think about something that you are doing that you can do a little bit better. I forgot to check, but yes.
The nets part, how exactly is that operations research related? It seems more like how the MS saying.
It's more just being aware of inefficiencies and taking advantage of inefficiencies.
So we saw like in a business, just an inefficiency that's maybe not related to linear algebra.
Linear algebra is just one of many tools that we can use. So linear programming is one tool. There are other tools we can use. Inefficiencies is a big thing. Is optimization, trying to do things better. I forgot to check which calendar we're using now. This was the 2013 to 2014 model. It's a little bit hard to see. I'll zoom in. Here's the 2013, where you see the beautiful month over here, and you have September and November. So what month do you think this is? October. Here's a 2014 month, October, and we have September. If you were going to have a calendar, would you want to see the previous month? So I actually did complain to Williams about how they were doing the calendars. I haven't checked to see if they've actually fixed this. But a lot of times, very small little things. How do you present information? What information do you choose to present? Real estate is precious. Here's one of my favorite plots. This is the year distribution of sunrise and sunset times in North Adams. This is roughly today. And if you notice, there's two discontinuities. It's not smooth. What is this telling us? Daylight savings. So clearly something is happening at those 2 points. Why is it moving so smooth here, except there? So always be aware. So here's another plot. So this is the distribution of who in the continental United States. Do we have anybody here from Hawaii or Alaska? Okay. Let me consider America. Okay. So distribution in 2018 of, no, I guess 2019, for the 2019 Super Bowl, who were people rooting for? So when you look at this, what can you tell me about where Patriots fans are? Or people who hate the Rams?
New England?
New England, okay. So clearly this part of the region of the country is special for some reason with respect to the Patriots. What else? Louisiana. Why? Louisiana.
The second time.
Yes, in the NFC Conference Championship, there was a blown call against the Rams, the team from New Orleans. And after the game, the defender who basically fouled and pulled the helmet to, I can't believe they didn't call me on it. And I think the NFL actually apologized for the blown call. Now, the Rams still had bad play calling beforehand, and they should not have been in that situation. There was a noticeable drop in number of people watching the Super Bowl in Louisiana that year. And in fact, a lot of bars, I have a friend who is a Pulitzer Prize winner who works on some of the papers there, they actually were going to bars and they were watching the old Rams Super Bowls rather than watching the current one. Does anybody notice anything else about this map? Yes?
Well, I was just gonna say it's from Memes website.
Well, no, but there's one other place about Patriot fans, yes.
St. Louis?
St. Louis. St. Louis right here is actually winning. Anybody know why? The Rams used to be, well, they used to be in Los Angeles, then they moved to St. Louis, and they moved back to Los Angeles. And so the people in St. Louis were still pissed that the Rams left. There is a lot of information typically available in maps and pictures and plots. And I really want you to get into the habit of looking at things carefully. All right. How many of you have seen Pascal's triangle? Okay, this is the 1, 1, 1, 1, 2, 1. What I want to do is I want to teach you a little bit about looking at things different ways. So what I'm going to do here is I'm going to show you Pascal's triangle mod 2. So what that means is if it's an odd number, I'm going to put a dot. If it's an even number, I'm going to just erase it. Now, normally we draw Pascal's triangle coming down like this. And as I draw more and more rows, I'm going to run into trouble because I only have, finite sized classroom. So what I'm going to do is I'm going to constantly be rescaling the image so that no matter how many rows I have, it's always in the same rectangle. The other thing, because of the program I'm using, it's actually easier to start not up here and come down, but to start on the left and have the triangle going out sideways. If it bothers you, just, take a little nap right now and put your head down on the table, and it should be fine. All right, and hopefully you will notice what we see. I should not have touched it. Okay. Oh, good, it went all the way back to the beginning. Wonderful. Take 2. Okay. So hopefully you are noticing a pattern here. A tremendous amount of structure in Pascal's triangle. So this is actually a fractal. Or maybe Darth Vader's Imperial Star Destroyer coming into play. The question is, how would you compute this efficiently? So a huge part of the class is to try to calculate things efficiently and well. It's not enough to have something if it takes so long to do the calculation that the Earth is going to die a heat death. So a lot of modern cryptography is along these lines, that if you try to do things by brute force, if every subatomic particle in the universe was a universe and every subatomic particle there was a supercomputer devoted exclusively to you, running since the dawn of the universe, it wouldn't be enough to make a dent in the calculation by brute force. So unfortunately, for a lot of the linear programming problems that we want to do, it will take so long to actually find the solution that the universe will be dead. You can't afford to wait that long. However, one of the very nice things about linear programming is that you can often get not a solution, but you can get an approximate solution in a very reasonable amount of time. So imagine you own American Airlines and you have revenue in the billions of dollars a year. And I can tell you within 2 hours of computation, here's the optimal schedule, and you'll be off by at most $50,000. $50,000 relative to $2 billion is nothing. Especially when you're trying to solve a problem and you don't even know if the values of the parameters that you're putting in are correct. You have to estimate things. So in a lot of the early math classes you take, you have an explicit equation to solve, you know what all the values of the parameters are, and you want to get the unique solution. Here, we don't even know the values of all the parameters we want to use. We do our best guess. We might do a sensitivity analysis and see how much a thing is going to change in terms of our answer, depending on how we change things. And there's a lot of times where you have bifurcation points, where a very small change leads to a tremendously different behavior. Anybody here physics? Okay, if I give you a pendulum, okay, I'm sorry? Yep, so you have a pendulum. Where's the equilibrium positions for the pendulum? I'm sorry? So I have a pendulum, it's rotating back and forth. Where can I release the pendulum and have it stay stationary? Where are the equilibrium points? I'm sorry?
Theoretically down in the middle and theoretically right.
Yeah, we have two. If the pendulum is perfectly straight up, it's an equilibrium position. It is a very unstable equilibrium position where a small movement is going to have wild swings now. If it's straight down, if you move it just a little bit, not going to be a big deal. So when you are doing a lot of things, you want to know how sensitive is your answer to the parameters you put in. If I have to know something to 6 decimal digits, am I going to be able to do that? For some things, yes. We have things in quantum mechanics that we know to 11 decimal digits, not a problem. For other things, no, we're not going to get 6 digits of accuracy. My father used to be an engineer, he then got his MBA, and he was in one class that was taught by a true theoretician who gave them an equation with 46 variables to describe what their business should do. And my father was trying to explain to her, look, some of these variables involve my own company. I don't even know what the values are for my own company for all these things, as well as the value for the competition, which we clearly do not have. How sensitive is your formula to these values? But isn't it beautiful? It tells you what to do. And he's like, mm-hmm. And he was smart enough to just nod and go, okay. So when you are doing things, it's important to know which things are extremely essential to observe well, and which things can you just be, order of magnitude is good enough. All right, we've got about 10 minutes left. Any questions on stuff up till now? All right, so we have a little bit of time left. So what I want to do for the last 10 minutes is talk a little bit about fast multiplication. And what I want to do is I want to take something that you've hopefully seen many times before and show you that you can do it better. Okay? You really want to be aware of what you're doing. A lot of times we do things just because, well, it's always been done this way. And if you stop and think for a moment, there's often a better way to do it. Okay, so typically multiplication is more expensive than addition. Imagine I give you 200-digit numbers, and frequently we work base 2. Computers love base 2. Well, if I have 200-digit numbers, if I want to multiply them, how many bit operations roughly is this going to be? Yes?
10,000.
10,000 or 100 squared. And if I wanted to add, it's roughly only going to be on the order of 100. Yeah, you have carrying and whatnot, but you can see that for multiplication, it goes like the square of the number of digits, whereas addition is more linear in the number of digits. So multiplication is going to be far more expensive. So I'm not going to really worry about the cost of addition. Okay? So imagine I give you a polynomial of degree 5, and I want to evaluate this. So the cost is going to be 15 multiplications. How many multiplications does it take to get x to the 5th? It's going to take 4 multiplications. X times x is x squared, times x is x cubed, times x is x to the 4th, times x is x to the 5th. That's 4 multiplications. Multiplied by 3, that's 5 multiplications. So the number of multiplications to evaluate f of x is 5 plus 4 plus 3 plus 2 plus 1 plus 0 is 15 multiplications. These are the triangle numbers, the sums of the first D numbers, where if you want, you can either start counting at 1 or at 0. My son realized when he was very young that Daddy's a mathematician. If I start counting at 0 and he says I can do something 3 more times, I can do it 4 times. So we can have 0 or not, it's not going to change the value of the sum. There's actually a nice way to calculate what the sum is. You can do it by induction, or the Gauss trick is you write the numbers backwards, and then 1 plus d is d plus 1. 2 plus d minus 1 is d plus 1. And you just keep marching down like that. And so you get twice the sum is we have d copies of d plus 1. So the sum is just d plus 1 over 2. So this is telling us that polynomial evaluation is essentially quadratic in the degree. Now, as a theoretician, it doesn't bother me. Just evaluate and you get some value. But if you actually want a computer to be dealing with things like this, and this is actually extremely important if you want to generate fractal pictures, can I evaluate this faster? And it turns out there's a better way. How many of you have seen Horner's algorithm? Right. This is having fun with the different colors you could do in tech. So what I'm going to do is I'm going to do grouping in parentheses. So I'm going to do 3x minus 8 times x plus 7 times x plus 6 times x minus 9 times x plus 2. And if you multiply everything out, I get 3x, 3x squared, 3x cubed, 3x to the 4th, 3x to the 5th. Ah, that's my 3x to the 5th chunk. The next one is going to be minus 8x squared, minus 8x cubed, minus 8x to the 4th. There's my minus 8x to the 4th chunk. And so by grouping it like this, it's now linear in the number of operations. It's only going to cost me d multiplications. It's a little bit more work to code maybe, but not terrible. And this is one of the main things I want you to get out of the course. That there's often better ways to do things than you've been doing before, and the savings can be tremendous. We go from something of order d squared to something of order d. Now for cryptography, we typically need to do stuff like this where d is of size 10 to the 400. So 10 to the 400, this is already universe of universes of supercomputers running since the dawn of time, can't make a dent in it. So we're still in trouble, we need to do better. So can we do better than this for polynomial evaluation? If you can find a better way, let me know. But there's something better. We don't have to be better all the time. Maybe it's enough to just be better for a certain class of polynomials. Can anybody think of a really nice degree D polynomial?
X plus 1 to the d.
I'm sorry?
I say x to the d.
X to the d. So maybe if we just try polynomial formula, I chose x to the n just to make it standard. So I always take n to be 100 because this way if I'm doing it on the board, I remember the binary expansion of n of 100 is 64 plus 32 plus 4. So the 2 here just means I'm working base 2. I have 0 1s, I have 0 2s, I have 1 4, no 8s, no 16s, 1 32nd, and 1 64. Any Futurama fans? Do you remember the episode where Bender the werewolf? So there was an episode, a lot of the writers from The Simpsons worked on Futurama. It's another cartoon. They have a lot of mathematicians who like to put little jokes in. So there's one episode where one of the characters, a robot, inherits a haunted house. And at one point you see a bunch of 1s and 0s in blood. And he asks the robot, what does this mean? He goes, I don't know. And then later the robot sees it reflected in a mirror and starts running away screaming. It turns out the writers took the number 666, the number of the beast, they wrote it in binary backwards. They go to tremendous lengths sometimes for math jokes. I actually have a colleague who wrote a theorem based on one of the episodes involving the Harlem Globetrotters. So I will talk about that maybe at some other point. So binary expansion of n, binary is wonderful. Look at how many multiplications it costs now to get x to the 100. It's not 99 multiplications. This is 1, 2, 3, 4, 5, 6 multiplications to get up to x to the 64. And then x to the 64 times x to the 32 is x to the 96, times x to the 4 is x to the 100. I can calculate x to the 100 in just 8 multiplications. And in general, this is going to take logarithmic time. So instead of doing d squared, which is a general polynomial evaluation, Horner's algorithm is order d. Well, if d is 10 to the 400, which is what you have for RSA encryption, it's still too much. Log d, however, that we can do. And so big theme for the class is how can you do things better? The last thing which I'll end on, since we have a minute or two, if possible, it's nice to have things explicit. Okay, so in mathematics, we have a bunch of questions. The first question is there a solution? The next question might be, is the solution unique or is there more than one solution? And then after that, it might be, what might you ask after that? Well, not quite optimal. So first I want to know, does the problem have an answer? Yes, good, it has an answer. Yes?
Is it better than the existing answer?
We might not even know an existing answer.
Is that like computable, really?
Is it computable? What is the answer? So there's a lot of things in mathematics which are constructive proofs, and there are a lot of things that are non-constructive, that are existence proofs, like the mean value theorem. There exists a point with the following properties. Doesn't tell you where it is. For a lot of things like proving the fundamental theorem of calculus, we don't need to know where it is. We just need to know that it exists. I do not want to go into politics in great detail. Let's just imagine that you have been hired by one of the many people running for president in 2020. And you say, good news! There's a path for you to get to 270 electoral votes and win the White House. Wonderful, what do I do? It's an existence proof. Your consulting career will be dead. I actually have a professor who was a consultant during the 2000 election fiasco. And I can talk about that when the camera is not rolling. But there are many things in life where if you just know an answer exists, that's often good enough. And a lot of theoretical math classes are like that. But in the real world, you often want to be able to say, can I actually find the answer? Well, if I can't find the answer, can I at least get close to the answer? So that's going to be one of our goals. All right, I think this is a good place to stop.
So you might-